The Brooklyn Bridge has 14,000 miles of steel cable suspended over the East River. That is enough wire to wrap the Earth's equator more than halfway. The cables were spun in place by hand in 1877 and 1878. The men who did the spinning worked on wooden platforms 300 feet above the river. The wires came from a Trenton, New Jersey wire works owned by the same family that designed the bridge. The cables are still holding the bridge up today, 14,000 miles. Read that number again. The Brooklyn Bridge does not have 4 cables of equal weight that look like solid steel rods. The Brooklyn Bridge has 4 main cables, each one approximately 15.75 inches in diameter, each one composed of 5,434 individual parallel galvanized steel wires bundled into 19 strands, then wrapped into the final main cable. Multiply 5,434 wires by 4 main cables by the bridge's main span of 1,595 feet, plus the side spans and the anchorage runs, and you arrive at approximately 14,000 miles of total wire length. Every single inch of that wire was spun in place over the East River in 1877 and 1878, using traveler wheels on overhead rails to carry each individual wire across the gap continuously, one strand at a time, day after day, for 26 months of continuous spinning operations. The Brooklyn Bridge cable spinning operation is one of the most extraordinary engineering achievements of the 19th century. It is also one of the most physically dangerous. Workers stood on narrow wooden platforms suspended approximately 300 feet above the East River. They had no safety harnesses. They had no hard hats. They had no electric lighting. They had heavy galvanized steel wire running through their hands at speeds determined by the traveler wheels on the overhead rail system. They worked in all weather conditions short of major storms, including high winds that swung the suspended platforms substantially. 3 workers died during the cable spinning operation specifically, falling from the platforms into the East River below. 24 other workers died during other phases of the bridge construction over the 14-year build period from 1869 to 1883. The total Brooklyn Bridge death count of 27 represents one of the lowest casualty rates among major American bridge projects of the late 19th century, but it was paid for in human lives nonetheless. The Roebling family designed and built the bridge. John Augustus Roebling was born in Germany in 1806, trained as a civil engineer in Berlin, emigrated to the United States in 1831, and built his career on iron wire rope manufacture and suspension bridge engineering. By the 1860s, Roebling was the most respected suspension bridge engineer in the United States. He had designed and built the Allegheny Suspension Bridge in Pittsburgh, the Niagara Falls Suspension Bridge between New York and Ontario, and the Cincinnati Suspension Bridge across the Ohio River. In 1865, the New York State Legislature authorized a private corporation to build a suspension bridge across the East River between New York City and Brooklyn. Roebling submitted the design proposal in 1867. Construction was authorized to begin in 1869. John Roebling personally surveyed the bridge site at the Brooklyn shoreline on June 28, 1869. He was standing on a dock supervising the alignment when a Fulton ferry boat collided with the dock and crushed his foot. The injury became gangrenous. Tetanus set in. John Augustus Roebling died on July 22, 1869, 24 days after the survey accident, at the age of 63. If you appreciate the depth of these American industrial heritage stories and want to support more of them, join at the Boss tier for early access and members-only polls, or Final Boss for member shoutouts and members-only videos. The link is in the description below. Now we walk through what happened after John Roebling's death and how his son Washington and daughter-in-law Emily took over the project. John Augustus Roebling's broader engineering legacy before his death deserves separate attention because it explains how the Roebling family had developed the specific technical knowledge that made the Brooklyn Bridge possible. Roebling had emigrated from Mühlhausen, Prussia to the United States in 1831 at the age of 25, originally settling in western Pennsylvania to establish a German immigrant agricultural community. The agricultural settlement struggled commercially, and Roebling turned to civil engineering work for various Pennsylvania canal and railroad projects through the 1830s. By 1840, he had developed the first American iron wire rope manufacturing process, initially produced at a small wire works in Saxonburg, Pennsylvania, and later expanded to the larger Trenton, New Jersey facility. The iron wire rope was used for canal portage railroad cables, mine hoisting cables, and various other industrial applications. The wire rope manufacturing experience gave Roebling deep technical knowledge of high-strength tension cable behavior. which became the foundation for his subsequent suspension bridge work. Roebling's first major suspension bridge was the Allegheny Aqueduct, completed in 1845 across the Allegheny River in Pittsburgh. The aqueduct carried the Pennsylvania Canal across the river on a wire cable suspension structure, with a wooden trough carrying the canal water along the suspended deck. The Allegheny Aqueduct was the first practical demonstration of wire cable suspension technology for major civil engineering work in the United States. The bridge operated successfully for 15 years before being replaced by a larger iron suspension bridge in the 1860s. The technical lineage from the Allegheny Aqueduct through Roebling's subsequent works to the Brooklyn Bridge is direct and continuous. Roebling's second major work was the Niagara Falls Suspension Bridge, completed in 1855. The Niagara Falls Bridge carried both railroad and pedestrian traffic across the Niagara Gorge between New York State and Ontario, Canada. The bridge was the first major railroad suspension bridge in the world, demonstrating that wire cable suspension could handle the heavy dynamic loads of railroad traffic. The Niagara Falls Bridge operated for 42 years before being replaced by a steel arch bridge in 1897. Roebling's third major work was the Cincinnati Suspension Bridge, completed in 1866 across the Ohio River between Cincinnati, Ohio and Covington, Kentucky. The Cincinnati Bridge was the longest suspension bridge in the world at completion, with a main span of 1,057 feet. The bridge is still in active service today, having been continuously operated for 159 years. Washington Augustus Roebling was 32 years old when his father died. He had served as a Union Army colonel during the Civil War, had spent 2 years studying European bridge construction in Berlin, Paris, and London during the 1860s, and had served as his father's chief assistant on the Cincinnati Suspension Bridge. He took over as chief engineer of the Brooklyn Bridge project within days of his father's death. The first major construction phase was the building of the 2 stone tower foundations in the East River bed. The tower foundations required pneumatic caissons. A pneumatic caisson is a large wooden box, open at the bottom, sealed at the top, that is lowered into the riverbed and filled with compressed air to keep water out. Workers descend into the caisson through an airlock shaft from the surface, then excavate the riverbed under the caisson to lower it deeper into the bedrock. The Brooklyn caisson was 31 feet below the East River water level. The New York caisson was 78 feet below. Both caissons had been sunk and filled with concrete by 1873. The problem with pneumatic caissons was a medical condition that 19th century engineers and physicians did not fully understand. When workers came back to the surface from a high-pressure caisson environment, they sometimes developed severe joint pain, paralysis, and in some cases death. The condition was called caisson disease at the time, or the bends because the joint pain made workers bend over in pain. Modern medicine calls it decompression sickness. It is caused by nitrogen gas dissolved in the bloodstream under high pressure forming bubbles in the blood and tissues as the pressure decreases during decompression. Nobody in 1872 understood the gas bubble mechanism. The treatment at the time was rest and warmth, neither of which actually helped. The only effective prevention was slow gradual decompression, which the Brooklyn Bridge crews started using on an ad hoc basis after some workers seemed to recover better than others. Washington Roebling personally supervised the caisson work in 1872 and 1873, descending into the New York caisson at 78 feet of water depth multiple times per week to inspect the excavation progress. In late 1872, after one particularly long inspection in the New York caisson, Washington came up to the surface and collapsed. He had severe joint pain, partial paralysis, and what his wife later described as nervous prostration. He never fully recovered. From 1873 onward, Washington Roebling was a partial invalid, confined mostly to his home in Brooklyn Heights, unable to walk to the bridge site, unable to climb on the construction platforms, unable to physically inspect the work. He was the chief engineer of the largest bridge construction project in American history, and he could not get out of his upper floor bedroom for the next 11 years. Emily Warren Roebling was 29 years old when her husband Washington was disabled by caisson disease. She had been born into a prominent New York family in Cold Spring on the Hudson, had received an unusually thorough education for a woman of her generation, and had been corresponding with her husband on engineering matters since their marriage in 1865. When Washington was confined to bed, Emily became his deputy at the bridge construction site. She visited the bridge daily for the next 11 years. She carried Washington's written instructions to the foreman. She studied Washington's engineering specifications. She gradually learned the technical content of the project so thoroughly that she could answer engineering questions from the foreman and the public on her own authority. By 1875, Emily Warren Roebling was effectively running the bridge construction project on behalf of her husband. The American Society of Civil Engineers in the 1870s had no women members and no provision for women members. The Brooklyn Bridge construction firm had no woman engineer on its formal payroll. But the project was being run by a woman regardless of those formal exclusions. Emily Roebling was the first woman in American history to manage major bridge construction. Her management of the project from 1875 to 1883 made the completion of the bridge possible. If you are new here and enjoying this kind of historical depth, subscribe so you do not miss the next video. We publish 2 videos per day this week. Now we walk through the cable spinning operation specifically and why it is the technical heart of the Brooklyn Bridge story. Emily Warren Roebling's specific engineering education during her years as her husband's deputy deserves more detailed attention because it represents one of the most remarkable self-taught engineering education stories in American history. Emily had received an unusually thorough education for a woman of her generation at the Georgetown Visitation Convent School, where she had studied mathematics, French, and classical literature through age 18. When her husband was disabled in 1873, Emily began systematic study of engineering with materials that Washington selected and explained to her from his bedroom. The curriculum included Henry Moseley's The Mechanical Principles of Engineering and Architecture, William Rankin's Manual of Civil Engineering, and various technical reference books on suspension bridge engineering, material science, and construction management. Emily studied these texts in the evenings while spending her days at the bridge construction site. Within 3 years, Emily had developed engineering knowledge sufficient to answer technical questions from foremen, contractors, and visiting engineers on her own authority without consulting Washington. The engineering correspondence Emily maintained with the bridge contractors, the New York City municipal engineers, and the broader engineering community during her years as effective chief engineer is preserved at the Rensselaer Polytechnic Institute archives in Troy, New York. The letters show Emily addressing detailed technical questions including cable tension calculations, anchorage stress analysis, deck truss design questions, and labor management issues. The correspondence is signed by Emily directly, not as her husband's representative. Engineering visitors to the bridge construction site routinely addressed her as the responsible engineer on the project. The American Society of Civil Engineers, founded in 1852, did not admit women as members during Emily's lifetime. But Emily was invited to speak at the Society's annual meeting in 1882 specifically about her work on the Brooklyn Bridge. She declined the invitation, but the offer itself was unprecedented for a woman in 19th century American engineering. The opening ceremony speech delivered by Abram Hewitt on May 24, 1883, included an extended public tribute to Emily Warren Roebling specifically. Hewitt was the New York congressman who had championed the Brooklyn Bridge project through Congress during the 1870s and who served as the official ceremonial speaker at the opening. Hewitt's speech included the lines, "The name of Mrs. Washington A. Roebling will be inseparably associated with all that is admirable in human nature and with all that is wonderful in the constructive world of art." The tribute was published in newspapers across the United States the following day. It was the first time in American history that a major engineering achievement was publicly credited to a woman engineer at the opening ceremony of the project. The cable spinning operation began in earnest in May 1877. The 2 stone towers had been completed. The cable anchorages had been built on the Brooklyn and Manhattan shorelines. The anchorages were massive concrete and stone structures that held the ends of the cables firmly against the loading of the bridge deck. Each anchorage contained approximately 20,000 tons of stone and concrete fill, with iron eye-bars embedded in the masonry to attach to the cable strand ends. The cables themselves had to be spun from individual galvanized steel wires across the East River and through the anchorages at both ends. The traveler wheel was the key piece of equipment for the spinning operation. A traveler wheel is a large wooden grooved wheel, approximately 8 feet in diameter, that rides on an overhead cable rail strung across the bridge from anchorage to anchorage over the tower tops. The traveler wheel carries a single steel wire in its groove, with the wire fed continuously from a reel at one anchorage, around the traveler wheel, across the river, around a return wheel at the opposite anchorage, and back to the original anchorage. The traveler wheel is driven by a steam engine on the anchorage end, pulling the wire across the river at controlled speeds. Workers on the bridge platforms grab the wire as it passes and guide it into the proper position in the developing cable bundle. As each wire reaches its position, the wire is clamped temporarily in place, and the traveler wheel begins another circuit with the next wire. Repeat this process 5,434 times for each of the 4 main cables. 6 months of continuous operation. Workers on the platforms handling wires, clamping them in position, bundling them into the developing strands, all while balanced on narrow wooden walkways 300 feet above the river. The Roebling family wire works in Trenton, New Jersey, supplied the galvanized steel wire for the bridge cables. John Roebling had founded the wire works in 1848, originally to manufacture the iron wire rope he used for his early suspension bridges. By the 1870s, under the management of John's other son, Charles Roebling, the Trenton Works was producing high-strength galvanized steel wire to specifications that John Augustus Roebling had developed personally over the previous 20 years. The wire was approximately 1/8 of an inch in diameter, galvanized to resist corrosion, and tested to a tensile strength of 160,000 pounds per square inch. That tensile strength was approximately 3 times higher than the wrought iron strength used in earlier suspension bridges of the period. The Brooklyn Bridge cable specification could not have been built using wrought iron at the planned bridge span and load. The Roebling family had spent 20 years developing the steel wire technology specifically for this project. The bundling process for the cables involved compressing the 19 strands of each cable into a tight cylindrical bundle, then wrapping the bundle with smaller diameter spiral wire that held the bundle together permanently. The wrapping wire was applied by a specialized machine called a cable wrapper, which traveled along the bundle as it ran across the bridge, spinning a continuous loop of wrapping wire tightly around the bundle. After wrapping, the cable was coated with red lead paint to protect against corrosion. The total mass of each completed main cable was approximately 780 tons. The 4 main cables together added up to over 3,000 tons of suspended steel. The towers had to be designed to hold that mass, plus the bridge deck, plus the live load of vehicle and pedestrian traffic. The Roebling Trenton Wire Works manufacturing process for the galvanized steel wire deserves separate technical description because the wire specification was the key engineering enabler for the entire bridge. The Trenton Works under Charles Roebling, John's son and the brother of Washington, produced approximately 14,000 miles of galvanized steel wire for the Brooklyn Bridge between approximately 1876 and 1878. The wire manufacturing process began with high-grade Bessemer steel ingots produced at Pittsburgh and Bethlehem steel mills, which were shipped to Trenton by rail. The Trenton Works rolled the steel ingots through a series of mill stands that progressively reduced the cross-section from the original 8x8-inch ingot down to a 1/4 inch round bar. The round bar was then drawn through tungsten carbide dies that progressively reduced the diameter further, from 1/4 inch down to the final wire diameter of approximately 1/8 inch. The drawing process work-hardened the steel substantially, increasing the tensile strength from the approximately 90,000 pounds per square inch of the original Bessemer steel to the approximately 160,000 pounds per square inch of the finished bridge wire. The work-hardened wire was then galvanized through a hot-dip zinc process to provide corrosion resistance. The galvanized wire was wound onto steel reels in lengths of approximately 1 mile per reel, then shipped from Trenton to the bridge construction site by rail and barge. Each individual reel contained approximately 1 mile of wire and weighed approximately 1,000 pounds. The total wire requirement of 14,000 miles meant approximately 14,000 reels of wire had to be shipped from Trenton to Brooklyn over the spinning operation period. The quality control process at the Trenton Works was extraordinary by 19th century standards. Each batch of wire was tested for tensile strength using a destructive sample of approximately 3 feet from each 1 mile reel. The tested sample was loaded in a calibrated tension testing machine until failure, with the breaking load recorded against the specified minimum. Any batch falling below the specified tensile strength was rejected and not shipped to the bridge site. Approximately 3% of the wire batches produced during the bridge construction period were rejected for failing tensile testing. The rejected wire was reprocessed or sold as lower-grade industrial wire to other customers. The quality control system was the reason the bridge cables have lasted so long. The Trenton wire that made it to the Brooklyn bridge cables had passed quality testing far stricter than any subsequent American bridge wire specification. The deck construction phase followed the cable spinning. The deck was a steel truss carrying the road, rail, and pedestrian surfaces. The deck steel was manufactured at multiple foundries across the eastern United States, including the Edgemoor Iron Works of Wilmington, Delaware, the Phoenix Iron Company of Phoenixville, Pennsylvania, and the Bethlehem Iron Works of Bethlehem, Pennsylvania. The deck assembly proceeded from the towers outward, with deck sections hoisted from the river by steam hoists and bolted into the developing truss. The deck assembly took approximately 4 years, from 1878 to 1882. Final assembly of the entire bridge structure was complete by April 1883. The opening ceremony was scheduled for May 24, 1883. The pneumatic caisson disease that crippled Washington Roebling deserves more detailed medical and engineering description because it shaped the entire second half of the Brooklyn Bridge construction. Caisson disease, now called decompression sickness, occurs when a person is exposed to high atmospheric pressure for extended periods and then returns to normal atmospheric pressure too rapidly. The nitrogen gas dissolved in the blood and tissues under high pressure forms bubbles as the pressure decreases, causing severe joint pain, paralysis, and in serious cases, organ failure or death. The condition was not understood medically in 1872 when Washington Roebling developed it. The treatment available at the time was rest, warmth, and various unhelpful 19th century medicines. None of the standard treatments were effective. The only effective intervention was slow gradual decompression during the return to the surface, which the Brooklyn Bridge crews began using on an ad hoc basis, after observing that some workers seemed to recover better than others. Washington Roebling's specific case was particularly severe because he descended into the New York caisson at 78 feet of water depth multiple times per week over an 18-month period in 1872 and 1873. The cumulative nitrogen exposure damaged his nervous system extensively. Modern medical analysis of his symptoms, based on the detailed correspondence he maintained throughout his life, suggests that he probably suffered permanent spinal cord damage from chronic decompression sickness, with additional symptoms of post-traumatic stress and chronic pain syndrome that compounded the physical disability. He never fully recovered. From 1873 until his death in 1926, Washington Roebling was a partial invalid, unable to perform sustained physical activity, requiring substantial daily medical care, and dependent on his wife Emily for the routine activities of daily life. The other Brooklyn Bridge caisson disease casualties beyond Washington Roebling included approximately 120 workers who developed clinical symptoms of caisson disease during construction. Of those, approximately 3 died directly from the immediate symptoms, primarily from cardiovascular collapse or stroke during severe decompression incidents. The remaining 117 survived, but with varying degrees of permanent disability. The total caisson disease casualty rate among the bridge construction workforce who worked the high-pressure caissons was approximately 20%, an extraordinarily high industrial disease rate. The Brooklyn Bridge construction was probably the worst single industrial disease incident in American 19th century construction history, even though the immediate fatality count was relatively low. Most of the caisson disease victims died of complications from their original injuries decades after the bridge construction ended. The opening ceremony drew an estimated crowd of 50,000 people on the Brooklyn side and another 100,000 on the Manhattan side. President Chester A. Arthur attended. New York Governor Grover Cleveland attended. The two cities of New York and Brooklyn, which were separate municipal entities until 1898, jointly funded the ceremony. Emily Warren Roebling personally led the first procession across the bridge in a carriage drawn by white horses. Washington Roebling watched the procession from the window of his upper-floor bedroom in Brooklyn Heights, 2 miles from the bridge approach, using a brass telescope his wife had set up for him. He did not attend the ceremony in person. He had not been able to leave the house for several years. The Brooklyn Bridge opened for full traffic the day after the ceremony. Initial traffic included pedestrians, carriages, horse-drawn streetcars, and the first cable car runs across the bridge deck. Total daily traffic in the first year of operation was approximately 300,000 crossings, including the cable car passengers, the pedestrians, and the carriage traffic. By the early 1900s, after the introduction of automobile and elevated rail traffic, daily crossings reached approximately 700,000. The current daily traffic count is approximately 105,000 vehicles, plus approximately 30,000 pedestrians and bicyclists. Anyone who has seen the masonry on a 150-year-old bridge knows this. The Brooklyn Bridge engineering was not just engineering. It was a particular generational achievement that combined 3 decades of Roebling family suspension bridge experience. 14 years of Brooklyn Bridge construction labor, the engineering management work of Washington and Emily Roebling, and the steel wire technology developed at the Trenton Family Wire Works. The bridge could not have been built without all of those components coming together at exactly the right time. John Roebling died before construction began. Washington Roebling could not physically supervise the construction after 1873. Emily Roebling carried the project across the finish line through 11 years of effective de facto chief engineer responsibility. The cables they built together are still holding the bridge up today. The opening day procession across the bridge on May 24, 1883, was a particular spectacle that deserves separate description. The procession was led by Emily Warren Roebling in a carriage drawn by white horses, accompanied by Governor Grover Cleveland and President Chester Arthur. The procession crossed from the Brooklyn approach to the Manhattan approach over the course of approximately 45 minutes, with the carriage moving slowly to allow the assembled crowds on both sides to view the participants. The carriage carried a live rooster that Emily had brought as a symbolic gesture, allegedly to ensure that the bridge would never become the property of New York City politicians. The rooster gesture was widely reported in the newspapers of the day and became part of the bridge opening folklore. The choice of Emily as procession leader was deliberate. Washington Roebling had specifically requested that his wife be honored as the de facto chief engineer of the project, and the Brooklyn Bridge Corporation Board had agreed. The bridge stampede incident of May 30, 1883, just 6 days after the opening, deserves separate treatment as one of the worst civilian disasters in 19th century American history. On Memorial Day 1883, a large crowd of pedestrians was crossing the bridge when rumors spread that the bridge was collapsing. The rumors were false, but the crowd panicked and a stampede occurred on the pedestrian walkway. 12 people were trampled or crushed to death, and dozens were injured. The stampede became a major political scandal, with critics arguing that the bridge was poorly designed for pedestrian safety. The Brooklyn Bridge Corporation responded by installing improved railings and pedestrian flow controls on the walkway. The stampede did not affect the bridge's structural reputation, but it did demonstrate that the engineering of large-scale public infrastructure required not just structural design, but also crowd management design. The Brooklyn Bridge has been continuously in service since its opening on May 24, 1883. The cables have not been replaced. The main steel cables of 1977 and 1978, the original Roebling galvanized wire from Trenton, New Jersey, the original wrapping and red lead coating, are still in place today. The cables have been periodically inspected by stress testing and X-ray equipment. The annual New York City Department of Transportation inspection reports document that approximately 5% of the original wire strands have developed corrosion damage over the past century and a half, but the overall cable strength remains within engineering tolerances. The bridge deck has been substantially rebuilt several times. The most recent major reconstruction was completed in 2021. But the cables, the load-bearing heart of the bridge, are the same wire that was spun into place during 1877 and 1878, more than 140 years ago. Before we close, if this kind of pre-modern engineering story is what you came for, the final boss tier at $9.99 gets you members-only videos plus your name in upcoming uploads. Boss tier at $4.99 for early access. Link in the description. Thanks for watching to the end. The Brooklyn Bridge cables are still holding the bridge up today, 142 years after the spinning operation completed. Emily Warren Roebling died in 1903 at the age of 59. Washington Roebling outlived her by 23 years and died in 1926 at the age of 89, never having fully recovered from caisson disease. The Roebling-Trenton wire works closed in 1974. The cables they manufactured are still operational. Approximately 105,000 vehicles cross the Brooklyn Bridge every day. The cable specification has never been matched by any modern suspension bridge cable manufactured to the same diameter and load tolerance. John Augustus Roebling's original design from 1867 has carried more total traffic than any other suspension bridge in American history. The bridge is the technical ancestor of every major American suspension bridge built since, including the Williamsburg Bridge of 1903, the Manhattan Bridge of 1909, the George Washington Bridge of 1931, the Golden Gate Bridge of 1937, the Verrazano Narrows Bridge of 1964, and the Mackinac Bridge of 1957. The Brooklyn Bridge fathered them all. The cables are still in the granite anchorages, still in the towers, still over the river. The records prove it. The wire holds.